So let's see now examples. Mainly this lecture will be about common source amplifiers. Okay, the first configuration of our MOS transistor amplifier circuits. And here we have example of a common source amplifier in which the input is at the gate and the output is at the drain. And of course, the source is common. This is common source circuit. So the threshold voltage of that transistor is 0.4, Kn is 4 milliampere, and VGS is 0.6. So this battery here is 0.6 volt. So find GM and AV, number A, and in number B, find the maximum swing at the input and the output. How far we can amplify, or how far can this input go? What is the maximum input that we can put? Remember, in amplifiers, we need always to work in saturation region. So we can't just put any input and expect that we have output, which is amplified version of the input, because we may go to saturation or cutoff. And in that case, we will just see clipping or distortion. Okay, so let's start by number A. Find GM and AV. So we'll have the DC analysis. And in the DC analysis, we're gonna verify that we are working in saturation. So we have to calculate ID, then calculate VDS. So ID, assuming saturation, is equal to Kn over 2, VGS minus V threshold square. So this is equal to 4 over 2, 0.6 minus 0.4 square. So ID will be equal to 0.08 milliampere. From the outer loop here, this is VDS, and this is IDRD. So if we just continue here, this battery is VDD. So from this loop here, we have VDS plus IDRD equal to VDD. So from this equation, VDS is equal to VDD minus IDRD. It will be equal to 0.4 volt. Let's compare it with VGS minus V threshold. So VGS minus V threshold is equal to 0.6 minus 0.4, it's 0.2. And of course, 0.4 is larger than 0.2, so it's really saturation. Now GM basically is Kn VGS minus V threshold. Kn is 4 milliampere per square voltage, and VGS is 0.6 and V threshold is 0.2. So this is basically 0.8 milliohm minus 1. Then we go to the AC analysis. And find, all the parameters of AC. So in AC, we're going to cancel all the DC sources, which is just one source here. It's two sources, VDD and VGS. So we'll end up with that circuit here. Here is RD. Here is V input or VGS small. See V input at the end. Okay, and here is V output. Then we're gonna replace the transistor by its equivalent circuit. So here is the drain. Here is the gate. Here is the source. Here is GM VGS, and here is VGS. Voltage between gate and source. And remember, there is nothing between gate and source. It's open circuit. Okay, this is a source. Between the source, it's just connected to ground. No. And between the drain and the ground, there is RD. And the voltage is the output is at between the drain and the ground. So here is the output. And between the gate and the ground, there is the input. So basically, number one, our input, because it's really easy, is just infinity. So our input is here. This is our input, equal to V input over I input. I input is equal to 0. So this is equal to V input over I input. So without, consuming much time, anything divided by 0 is infinity, right? Which is very good thing. So the basic advantage of common source amplifiers, it has a very high input resistance, very high. And this is, a common characteristics of most amplifiers, because the gate source resistance is infinity. It's a capacitor. And this is also a basic advantage of most transistors in general compared to BJT transistors. Good. Number 2. RO. Gonna put here a source at the output terminal. It's called Vx, which produces a current called Ix. Then we will have RD. And the GM VGS, and we're gonna cancel the source V input, so it will be short circuit. So VGS now, this is equal to Vx over Ix, is equal to 0. So the current source VGS GM is also equal to 0. So it's just open circuit. So the current Ix will just go here in RD. So Vx over Ix is equal to RD. And this is moderate to high. So till this moment, this is an advantage because it's very high, which is good. But this is not advantage. Moderate to high, this is bad. And in here, it's MOSFETs is similar to BJT, or common source is similar to common emitter. Both they have moderate to high output resistance, which is bad. Number 3 is the AV. AV is just equal to VO over V input. If we look here, this is the current that flows in RD is just GM VGS, but this will make a voltage drop positive, negative, positive at the ground and negative at VO. So VO is minus GM VGS RD, and the V input is just equal to VGS. Same terminals. This is the terminals of V input, and this is the terminal of VGS. So same terminals. So this will go with this minus GMRD. In our case here, GM is 0.8 milli. Okay, so 0.8 milli ohm multiplied by 17.5 kilo. So let's do this together. I think I have it. Yeah, it's minus 14. And yeah, it's low. It's not good. Like it's not very high. Like BJT transistors, common emitter BJT transistors, usually lower, but they have the same phase shift out of phase, 180. Good. But of course, this can be fixed by, for example, choosing higher resistance, higher RD. Okay, so we can fix that. So this is all number 1 or number A. Now number B, the maximum swing in VO and V input. Remember the transfer characteristics? Was something like this. This is VGS, V small GS capital because it's both AC and DC. And this is VDS, V small DS capital. Okay. This point is at V threshold, which in that case 0.4. This point we don't know, it's VGS SAT. And now we are working at that point at 0.6. If we go back here, VGS is equal to 0.6. Yeah, 0.6. And VDS is 0.4. So at this point, we have 0.4. So basically, we can put signals until we reach either VGS or 0.4. We don't know. If VGS, for example, is 2, then we can go forward by 2 minus 0.6, which is 1.4. But backward, that part is only 0.2. So we are restricted by in decreasing V input by V threshold. And we are restricted increasing V input by VGS SAT, the input at which we go into saturation. So there is limits. And this question here is to know the limits. What is this limit? Of course, if we know that VGS SAT minus 0.6 is larger than 0.2, which is 0.6 minus 0.4, then the limit is 0.2 in input. And we can calculate the corresponding swing in the output. Good. So what we know is that at that point, if we assume that we have an EC like this, the output will be something like this. So this is the minimum, VDS minimum, at which we go to the maximum here. So this change here, let's call it VDS minimum. It happens when VGS increases from that point to that point. So let's call it this VGS maximum. So VDS minimum happens at when input increases to VGS maximum, V small, GS small maximum. Or we can say V small, DS capital, the signal, the whole signal, AC plus DC minimum happens at V small, GS capital maximum, the whole signal, AC plus DC. And we know we shouldn't leave the saturation region. So VDS minimum must be larger than or equal VGS minus V threshold. But what is VDS minimum? It is something in DC plus something in EC. So the DC is V capital, DSC capital, which is 0.4, this point. Minus this portion, minus AV as a magnitude, multiplied by VGS maximum. Remember, we decreased when VGS increased because they are out of phase. Remember, when this is increasing, this is decreasing. You can say it's VDS plus EV VGS maximum, and you know EV is minus, so it will be minus at the end, right? Larger than VGS V small GS capital. This is G maximum here. Equal to V capital GS capital is the operating point of VGS, which is 0.6, plus V small GS small maximum minus V threshold. This is 0.4. This is how much? Minus 14, so it will be 14. Multiplied by VGS maximum, which we want to determine. Larger than or equal VGS capital, which is 0.6, plus VGS small maximum, minus V threshold, which is 0.4. And from that inequality here, we're gonna find that VGS maximum is equal to 13 millivolt. Very small. So the maximum input is 0.6 plus 13 milli, which is 0.613. And the minimum input is 0.6 minus 13 milli. Okay. And this will be corresponding to AV magnitude VGS maximum. So it will be 14 multiplied by 13 milli. So this is VDS minimum, or VDS small minimum. And of course, minimum will be like the max, it's a symmetrical signal. So peak to peak input is 13 millivolt multiplied by 2, which is 26 millivolt. And the peak to peak output will be 14 multiplied by 13 millivolt multiplied by 2 as well. Okay. So this was the first example. Let's take another example. Here ID is known, equal to 0.5 milliamperes, and V threshold of that transistor is 1 volt, and the Kn is 1 milliampere volt squared, and VDD is 15. Find AV, R input, and R output. Okay, first is DC analysis. So the capacitors are open circuit here and here. Okay, so VG will be equal to 15. Remember, the current here is 0 in the gate. So this is series with this. RG1 is series with RG2. So VG is equal to 15 multiplied by RG2, which is RG1, by the way, is 7 mega ohm, and RG2, I'm sorry, and the RG1 is 8 mega ohm. We usually choose them very big like this, and this for some reasons that we're gonna see afterwards. So VG will be 15 multiplied by 7 mega ohms, over 7 mega plus 8 mega. So 15, 7 over 15, it will be 7 volt. And Vs, the voltage at that point, is basically the voltage of the resistance. And remember, we know the current. The current is given, ID half milliamperes. So Vs is equal to ID Rs. So it's equal to half milliampere multiplied by Rs is 10 kilo ohms. I forgot to put it. And also RD is 10 kilo ohms. So 10 multiplied by 10, half multiplied by 10 kilo, it will be 5 volt. So VGS, which is VG minus VS, is equal to 2, or 5, or 7 minus 5 is 2 volt. VD, this point here, is equal to 15 minus the voltage drop across RD. So 15 minus ID RD. So 15 minus half and 10, this will be 5 volt, 10 volt, I'm sorry. Or 5 volt, yeah. 5 volt. Oh, 15 minus 5 is 10. Yeah. So 10 multiplied by half is 5, and 15 minus 5 is 10 volt. Okay, so VDS is equal to VD minus VS, 10, and VS is 5. So this is 5. And this is basically larger than VGS minus V threshold, which is 2 minus 1, which is 1. So we are working in saturation. And GM is equal to Kn VGS minus V threshold. VGS is 1, and VGS minus V threshold is just 1 as well. So GM is 1 milli ohm minus 1, because Kn in milli. Number 2, let's now draw the AC equivalent circuit. So we start first by the equivalent circuit of the transistor. GM VGS. Here is VGS between the gate and the source, and here is the drain. Okay, between the drain and the ground there is RD 15. And here is VO between the drain and the ground. And between the source and the ground there is a resistance RS. And between the gate and the ground there is RG1 and RG2 parallel. So I will call them RG. And there is a source input, V input. Let's call it V input. And the RG here is RG1 parallel RG2, the 7 mega ohm parallel with 8 mega ohm, which is basically 3.73 mega ohm, which is very big, really. Okay, number 1, find R input. R input is equal to RG. So here is V input. Here is I input, or let's call it I, or IG, parallel V input over IG. So basically our input is from these 2 points, this point and the ground. So it's equal to RG parallel this the resistance here, which is V input over IG. IG is 0. Anything divided by 0 is infinity. So RG parallel infinity is just equal to RG, and RG is RG1 parallel RG2, which is 3.73 mega ohm. Very big input. Very big R input. Very big. As I said, MOSFETs usually have very big input resistances, which is good. Number 2. AV. AV is VO over V input. VO is the voltage across RD, so it's equal to the current that flows in RD. Remember, VGM, VGS is flowing from down to up, so it makes a voltage opposite to VO. So this minus GM, VGS, RD, divided by V input. Where is V input? The input is between this point and the ground. So it's equal to, so from that loop here, it's equal to VGS plus this voltage, which is this current multiplied by the resistance. What is this current? It is just GM VGS, because this current come here and there is open in that branch, and so it will continue as a whole to that branch RS. So this is GM VGS RS. VGS with VGS with VGS will go away. So this will give us minus GM RD over 1 plus GM RS. And remember here to check on yourself. What is the new thing here, in opposite to the last example? The new thing here is RS. In the last example, the source was connected directly to ground. So EV was just GMRD. So what happens here if we put RS equal to 0 in that equation? If we put RS equal to 0, it will be minus GMRD over 1 plus 0, which is 1. So it will be minus GMRD, and that's it. Okay? So we can also calculate that, because we know GM, we know RD, and all other stuff. So it will be minus 10 over 11, which is 0.91. It's less than 1. There is no amplification here. There is no amplification. And RS has a similar effect like RE, the degenerate resistance. If you guys remember, in the common emitter, when we put RE, a resistor between the emitter and the ground, usually the EV reduces by some factor that is proportional to RE. Here, it's also reducing by a factor proportional to RS. Okay, number 3, RO. With RO, we put our Vx that degenerates by X between the output terminals. So the output is between these 2 points, this point and the ground. Then we have RD. Then we have this guy. GMVGS. And we have RS. How about the other part? So in the other part, we're going to cancel V input, since we put Vx and Ix. So we cancel the output. So it will be something like this. Here is RG. Remember, here is VGS. So what happened? RG is in parallel with a short circuit, so it will be shorted, right? So we can just remove, let's draw it again. So this will be something like this. Vx, and here is Ix, RD, and this will be just ground like this. So this is basically the gate, because the gate is just connected to ground now. And here is VGS. So, what is the voltage across RS from that loop? RS has a voltage, negative, positive, which is just VGS, right? Which will produce current in that direction. This current is equal to VGS over RS. So in that branch, this branch here, there is a current going down, which is GM VGS. and another current going up. So at that point, both currents are going into the point. So does VGS over RS equal to 0. So from that, VGS GM plus 1 over RS equal to 0. So either VGS equal to 0 or GM plus 1 RS equal to 0. Of course, GM is not equal to 0. And RS is a positive number and doesn't equal to 0 as well. So this can't happen. So VGS can equal to 0. So if VGS is equal to 0, so the current source GM VGS is equal to 0 as well. So it's open circuit. So this whole circuit here can be reduced to the following: Vx, Ix, and Rd. That's it, because now this guy is open circuit. So Ro, which is equal to Vx over Ix, is just equal to Rd. Which is 10 kilo ohms.